Hello everybody, I'm here with an example of kinetics of particles, and we have a problem here that we could easily solve this problem actually using work energy principle, but the objective right now is to solve this problem by second law. So our objective is using second law, F equal ma, right, to solve this problem. So let's get more information about this problem. And in this case, we have a color which is 2 pounds. So the weight of the color is 2 pounds. And you have to be careful, guys, again, with the unit, again, pound versus kilogram. And this is moving, or is given an initial velocity of 15 feet per second, right, as you could see in this picture, 15 feet per second, and is attached to a spring whose stiffness is 4 pounds per foot, right? And the spring, we are told that is unstretched when s equals 0. So basically, this is s equals 0 here, right? And the spring is undeformed when s is 0. So basically, the undeformed length of the spring, if I call it delta, is 1 meter, 1 foot rather, as you could see in the picture here. Okay, so the question is that if we give this an initial velocity of 15 feet per second, what would be the velocity of the color, this 2 pound color, as it reaches position s equal 1? So let's say if this is s equal 1, so this is 1 foot. What would be velocity at point C, or you can call it velocity 2 if you want. So find V when S is 1 foot. So remember, guys, I want to emphasize that this is like a 2-minute problem if you want to use the principle of work energy. So you'll see the difficulty if you want to use the second law. So if you're given a problem like this, don't even waste your time trying to use it. Use F equal ma, just use work energy. And I'll come back and I show you the same problem, and you'll see how easy it is to use work energy principle as opposed to, second law. By the way, we have to mention here that there's no friction here. So this, the contact between the color here and this surface is smooth. All right? So what we have to understand here is that acceleration here is not constant. In fact, you'll see that acceleration is a function of position here. Because as this guy moves, the force of the spring keeps changing. And as a result, the acceleration, or deceleration, I should say, is a function of position, where that color is and how much the spring is deformed. So don't try to get a constant acceleration and try to do that. And that's the catch for this problem, guys. Acceleration is going to be a function of position. So let me show you how we can find the acceleration. If you draw a free body diagram, by the way, and you have to draw a free body diagram at any arbitrary position, not at position 1, because that would be the acceleration at 1. We don't want that. We want to see how acceleration is changing from 1 to 2. Okay, so if we call this the force of the spring, I call it F sub x, and I'm going to call this angle theta, and I'm going to come back to this angle in a minute. You'll see how I'm going to describe that angle, or cosine of that angle, which I need, as a function of position. This is the weight, which is 2 pounds. Be careful, the weight is 2 pounds. There is a normal force, which is really not important to us. Now, I want to go ahead and find, because obviously I'm going to write the equation F equal ma in the x direction, in this direction, right? And by the way, there's no friction. That's why I didn't put anything in the horizontal direction. All right, so F sub s, guys, has to be multiplied by cosine theta, and it's acting in the negative direction. So this is basically this component of the spring force. And that is equal to mass times acceleration. So question is, what is F sub s? F sub s is k times how much the spring is deformed, which you can call that x or whatever you want to call it, for example. Or eventually we're going to write it in terms of s. So if I draw a picture here for you guys, so if this is, remember this distance, vertical distance is 1, it doesn't change. This is S, this is arbitrary. So this is where I'm drawing the free body diagram at this instant. So you see how the hypotenuse of this guy becomes the square root of S squared plus 1. Therefore, cosine theta, guys, first of all, cosine theta becomes adjacent over hypotenuse. And the other thing is, what is the amount of deformation x? The amount of deformation x is whatever the length of the spring is, this one, which is the hypotenuse, right? Minus the undeformed length. And the undeformed length, guys, is what? 1 foot. Remember, the problem told us. So force of the spring is going to be K, which is 4 pounds, times this guy, square root of S squared plus 1 minus 1. So now, if we plug in here, remember, that's the force of a spring, 4 times square root of S squared plus 1 minus 1, times cosine theta, which is S divided by square root of S squared plus 1, equal mass, be careful with the mass, guys, 2 divided by G, okay? Let me put a circle around this again. All right? So now if you clean this up a little bit, you will see that acceleration actually, let me see if I could do this for you. The acceleration, actually we can just get acceleration equal to, I believe it's 64.4. If I factor that out, we end up getting an S, if you multiply it out, minus S divided by, and by the way, this is in the negative direction, that's what I forgot, minus plus S divided by square root of S squared plus 1. Here we go, that's your acceleration, and that's exactly what I was trying to show you. Acceleration is going to be a function of position. You guys remember, when acceleration is a function of position, what do you have to do? Remember, acceleration is dv dt, but at the same time is what? V dv ds. Therefore, a ds, if you do a cross multiplication, a ds is equal to v dv. And now you could go ahead and plug in. So when position is 0, which is right here, velocity is 15 feet per second. When position is 1, which is here, what is velocity? So remember, you got to plug in for acceleration. Remember, acceleration is minus or 64.4 times minus s plus s over square root of s squared plus 1, right? ds, evaluated from 0 to 1. And over here, the integral of v dv, by the way, becomes 1/2 v squared, and this one should be easy. You just have to plug this in your calculator and figure out what the outcome of this integral is. Or actually, you could do it into by integration by parts. Either way, either by your calculator or just doing it manually yourself, velocity should be 14.6 feet per second, which is not much different than 15. And notice that I mentioned that this collar, the 2-point collar, is going to slow down, right? That's why the speed is going to be less than 15 feet per second. So we went through a deceleration. So this is actually a deceleration. Usually what the spring does is that it slows down the system. Okay, again, I want to emphasize that if you wanted to do this problem, and we'll see this in the soon in another chapter or another video, that by using work energy, this problem is much easier. So you bypass calculating acceleration. Why do we need to calculate acceleration? We can actually, by work and energy, just solve for velocity directly. Okay, guys, hope you enjoyed this video. I'll come back and I'll show you the work energy version of this problem, and you see how simple it is and quick it is to solve for velocity. Okay, as always, thank you for watching and listening.